Hello and welcome to this plastics training session. In this video, we will cover Module 2, Unit 2.4, that is Hydrothermal Liquefaction of Plastic Waste for Olefins Recovery, a techno-economic feasibility study. The focus of this module is to explore whether hydrothermal liquefaction, also known as HTL, can provide a viable pathway to convert plastic waste into valuable olefins while also assessing the financial return and sustainability. This is the plastics team from the Catalysis Engineering Group of Van Institute for Molecular Sciences at the University of Amsterdam. The group is led by Dr. Shiju Ravindran, who is also the principal investigator. Starting with myself, I am Dr. Roni Mallick, currently working as a postdoctoral researcher at the University of Amsterdam. Within the plastics project, I contribute to work package 3, where I focus on process understanding and modeling techniques. My research background includes waste valorization, techno-economic assessment, and life cycle analysis, which together help to evaluate the technical, economic, and environmental feasibility of HTL-based recycling pathway. To support this work, I use a range of modeling tools, including Aspen Plus for process simulation, MATLAB for reaction kinetics, and COMSOL for computational modeling. So, what is HTL? Hydrothermal liquefaction is a thermochemical conversion process that operates in hot, pressurized water, typically at temperatures above 400 degrees centigrade and high pressures of 180 to 220 bar for plastic waste, which yields oil and gas products. Under these conditions, water acts as both solvent and reactive medium. One key advantage of HTL is that it can process mixed and contaminated waste streams, which are often unsuitable for conventional mechanical recycling. To recover high-value chemicals, HTL can be integrated with downstream cracking units, enabling the conversion of HTL-derived oils into olefins, including ethylene and propylene. At the lab scale, the feasibility of this approach has been demonstrated in our lab at the University of Amsterdam, as shown in recent work by Chen et al. Building on these experimental insights, the commercial viability of HTL-based plastic to olefins has also been evaluated through a detailed techno-economic analysis conducted by me. This slide shows the mixed municipal plastic waste used in this study, with its composition present on the right-hand side. The waste sample was supplied by Cogersa, a partner in the plastics project located in Asturias, Spain. To better understand the behavior of this feedstock, we performed a detailed physical and chemical characterization. This includes proxiped analysis, which provides information on moisture, volatile matter, and ash content, and ultimate analysis, which determines the elemental composition of the waste. These properties are essential inputs for process design, modeling, and performance evaluation. Now I'm going to discuss about the experiments from HTL of plastic waste in our lab at the University of Amsterdam. The bigger picture of experimental process summarizes the product distribution carried out at temperatures between 430 and 460 degrees centigrade, pressures of 150 to 210 bar, and reaction time of 1 to 60 minutes. Under this condition, the process produces 10 to 30% of gas, 70 to 90% of oil, and a relatively small amount of char between 1.5 and 4%, along with recovered process water. However, if we take an example of HTL product yield as a function of reaction holding temperature, the process yields oil of approximately 85% at 430 degrees centigrade, while char formation remains minimal at around 1%. As the reaction temperature increases to 460 degree, the oil yield drops by nearly 10%. This trend can be explained by overcracking of the oil into gaseous product under more severe conditions. In terms of oil composition, lower temperature favor the formation of saturated alkenes, accounting for nearly 80% of the oil. With increasing temperature, the aromatic content rises, which is likely due to secondary cracking and aromatization of lighter oils or gaseous hydrocarbons. Extending the experimental results for downstream application, This slide outlines the overall HTL of plastic waste to olefin process, which is divided into 5 main stages. First, the HTL system converts mixed plastic waste into a hydrocarbon-rich oil and gas products under a very high temperature and high pressure water condition as discussed in the previous slide. This step serves as the primary conversion stage. Second, the HTL derived oil is sent to a steam cracking unit where it is thermally cracked to produce light hydrocarbons, particularly olefins such as ethylene and propylene. Third, the cracked gas stream is rapidly cooled in the gas changing section to stop further reactions and prevent undesired secondary cracking. Next, the gas is cooled and is processed through distillation and fractionation columns, which separate and purify the individual product streams of hydrogen and C1 to C4 light hydrocarbon gases, enabling recovery of target olefins. Finally, the steam turbine unit recovers energy from high-pressure steam generated from the heat within the entire process, improving the overall energy efficiency and reducing operating cost. Considering the previous slide of process description as reference, the energy and economic performance of the HTL of plastic waste to olefins was carried out in Aspen Plus software. This software is generally used to simulate industrial process and help to understand mass and energy balance of any thermodynamic systems. The present analysis is based on a plastic waste feed rate of 73,000 tons per year with a project lifetime of 25 years and 8,400 operating hours annually, representing a continuous operation. From an energy perspective, the process achieves an overall energy efficiency of 68%, while the electric efficiency is relatively low at 1.35%, reflecting the high energy demand of the process. In terms of economics, the estimated production costs are 1.55 euros per kg for ethylene and 2.64 euros per kg for propylene. The total capital investment is about 162 million euros with direct cost, that is equipment cost, installation, building, etc., accounting for nearly 80%, while the annual operating cost is around 29 million euros. The process shows promising performance with a return on investment or ROI of 8% and a payback period of approximately 3 years, indicating that HTL of plastic waste to olefins can be both energetically and economically feasible under the SS condition. The economic performance of the present study is also compared with reported literature values as shown in this table. For ethylene, conventional naphtha-based steam cracking shows production cost close to 2 euros per kg, while electrified steam cracking is slightly higher. However, in this study, an ethylene production cost of 1.55 euro per kg is achieved, which is lower than conventional fossil fuel-based routes. For propylene, a similar trend is observed. The HTL-based route in this study results in a production cost of 2.64 euro per kg, which is comparable to other waste-derived pathways reported in the literature. However, targeting mixed product is more economically beneficial because it avoids product separation and purity. So overall, this process comparison shows that HTL of plastic waste or mixed plastic waste integrated with steam cracking is economically competitive with established technologies and literature reported recycling routes. The following points are the key takeaways from the study, that is the HTL experimental product yields and energy efficiency and production cost to convert plastic waste to olefins. Before concluding, I would like to acknowledge the key references that were used for this work. These include recent studies from our catalysis engineering group, such as Boyle et al., which reviewed insights of HTL technology, Chen et al., who demonstrated lab-scale HTL of HDP-based waste, and Mallick et al., which reported techno-economic assessment for commercial feasibility. This concludes Module 2. Coming up next in Module 3, policy alignment towards a coherent and supportive framework for plastic recycling. Thank you for watching this training video. Stay tuned for the next module where we will continue exploring innovative technologies for circular plastic value chains.